All right, implicit differentiation. Let's do it. So what we're dealing with here is when you have not a function of x, but you have an equation that involves x and y that isn't easily solved for y. And just take a look at example number 1 right there. There's no way you're going to solve that for y. So we still want to be able to find the slope of the tangent line at any point along that graph. So what we could do is we can use what's called implicit differentiation. So before I do that, I just want to remind you about derivatives in the chain rule. So I'm just going to go off to the side over here. Let's say when you take the derivative with respect to x of something like x cubed, we know that's 3x squared. When you take the derivative with respect to x of something like y cubed, that's a little bit different. The idea here is that x is the variable. Since I'm taking the derivative with respect to y, it is assumed that y is in fact a function of x. So when we take the derivative of y cubed, we're going to really be taking the derivative of the function y of x. This is a function within a function. So by the chain rule, I bring that 3 down, make it a 2, inside stays inside, and then I have to multiply by the derivative of the inside. So in simplest form, when we take the derivative of something like y cubed, what we're going to get is 3y squared times the derivative of y with respect to x. That is just the chain rule. All right, so with that in mind, let's go ahead and take a look at this first problem here. So I'm going to start by taking the derivative with respect to x of everything in this equation. So it's going to go right across the line, taking the derivative with respect to x. So y to the 4th has a derivative of 4y cubed multiplied by the derivative of y with respect to x. Just a little warning to you here, this problem is going to take up a lot of space. That's the reason I'm writing so small. So derivative of y to the 4th, 4y cubed dy dx. This is a product, so when I find that derivative, I'm going to have to use the product rule. First, derivative second. So derivative of y to the 5th is 5y to the 4th times the derivative of y with respect to x. And then I have to add to that the second function, y to the 5th, times the derivative of the first, which is 3x squared. So here's my first, derivative second, second, derivative first. Keep going, derivative of negative 2x to the 7th, negative 14x to the 6th, and then the derivative of 13 is 0. So now what I've got here is an equation that has dy dx's in it. All I need to do now is solve this for dy dx. So the way I'm going to do that is I'm going to start by first getting the dy dx terms on the left-hand side. And if you peek up here, up at the top, I've actually got these guidelines written down. Number 1, differentiate both sides with respect to x. That's what I've already done. Number 2, collect dy dx terms on one side, all other terms on the other side. So that's what I'm going to do next. So I've got these two terms, which I'm going to highlight in yellow, that involve dy dx. Here's 4y cubed dy dx, and here's x cubed times 5y to the 4th dy dx. Those are the only two terms that involve dy dx. So I'm going to keep those two terms on the left-hand side of the equation. So I'm just going to go ahead and rewrite those. So let me tone down that. All right, 4y cubed dy dx plus, I'll rearrange that a little bit and make it look nicer, 5x cubed y to the 4th dy dx. Now these other terms, I'm going to move them to the other side of the equation by adding 14x to the 6th and subtracting 3x squared y to the 5th. So now I've got my dy dx's on one side, my non-dy dx terms on the other. Sneak back up here for a peek. After we've done this part, we're now going to factor out the common dy dx and then solve for it. So back to my question here. On the left-hand side, to isolate dy dx, I'm simply going to factor out the common dy dx. 4y cubed plus 5x cubed y to the fourth. So I pulled out that common dy dx, and on the right hand side I've got 14x to the sixth minus 3x squared y to the fifth. And then the last step is to simply divide both sides by what's in the parentheses. So let me just slide over here, zoom this out a little bit. I'm going to head back over here and go a little bit thicker so you can see it. When I divide both sides of the equation, I'm going to end up with the following. dy dx is equal to what's on the right hand side, 14x to the sixth minus 3x squared y to the fifth, and then that's all going to be divided by what's in the parentheses there, 4y cubed plus 5x cubed y to the fourth. So there is my derivative using implicit differentiation. Now when you use implicit differentiation, you are going to end up with both x's and y's in your derivative, because we're starting with an equation that involves both x's and y's. So if you were given an xy value, you could now substitute it in there and get that slope value. All right, let's continue on. Here I've got a simpler equation, but still one that's not going to be easy to solve for y. So I'm going to go ahead and use implicit differentiation again. This time we're going to want to find that derivative at -1, 2, and then we'll write the equation of the tangent line. So let's start with the equation. I'm going to do as I did before. I'm going to go ahead and take the derivative with respect to x all the way across the equation. So let me just rewrite that over here. So we're going to take the derivative with respect to x of this entire equation all the way across term by term. All right. So here we go. Derivative with respect to x of x squared, 2x. Here, once again, I have a product of x and y. So I'm going to subtract the derivative of that product. First derivative second plus second derivative first. Derivative of y squared, 2y dy dx. Derivative of 7, 0. Let's distribute this across. 2x minus x dy dx minus y plus 2y dy dx is equal to 0. Now, as before, I'm going to identify the terms that have dy dx. Keep those on the right. On the left. Move the other terms to the right-hand side. So I've got my negative x dy dx. I've got my 2y dy dx. And now I'm going to subtract 2x to the other side and add y to the other side. Next step, as before, come up here, factor out the common dy dx, leaving behind a negative x plus 2y, still equal to negative 2x plus y. Divide both sides by negative x plus 2y, and I'll have my derivative. dy dx is, let's see, I'm going to rearrange this just so my positives come first. So y minus 2x over 2y minus x. All right? Now, this time we don't just want the derivative, we want a tangent line. So I'm going to use the point -1, 2 to get my slope. So dy dx evaluated at -1, 2. So that's the notation that we use. And I'm just going to plug in -1 in each instance of x, 2 in each instance of y. So 2 minus 2 times -1 over 2 times 2 minus a -1. So that's going to be a positive 4 over a positive 5 4/5. So there's the slope of the tangent line. Now to write the equation of the tangent line, just go to your point slope form with your x and y. So y minus the y coordinate is equal to 4/5 x minus the x coordinate, and there is your tangent line equation. So we use implicit differentiation to get that derivative, which is right there. And then I substituted in the x and the y into that to get the slope, and then wrote the equation of my line. Okay. Let's see. I want to jump down to number 4 here just because this one this is just a review question, doesn't really involve implicit differentiation. So why don't we go down to number 4? So number 4 here, I've got the equation. This is the equation of a circle of radius 5 centered at the origin. I want to find the second derivative at the xy coordinate point 4, 3. So let's start by go ahead and taking our derivative with respect to x all the way across. So derivative with respect to x of x squared is 2x. Derivative with respect to x of 2y is 2y dy dx. And the derivative of 25 is 0. Solving that for dy dx by subtracting the 2x and dividing by the 2y is going to get me to negative x over y. Now that is the first derivative. I want the second derivative. And the way you get a second derivative is by taking the derivative of the derivative. So the second derivative of y with respect to x is going to be found by taking the derivative of my derivative, which is going to require the quotient rule. So low d high minus high d low all over low squared. Now I don't really want my derivative in my second derivative, so I'm going to replace dy dx with what it's equal to in terms of x and y. So coming back over here, this is going to be equal to negative y plus x, double negative, multiplied by negative x over y all over y squared. Now to simplify this fraction within a fraction, I'm going to eliminate this y by multiplying by y, and then to make up for it in the denominator, I'll also multiply by y. Distributing that through is going to get me a negative y squared minus an x squared all over y cubed. Now, if I notice here that I have x squared and y squared negative, up here in the original statement of the problem, right here, I've got x squared plus y squared is equal to 25. If I factor out a negative 1, then that x squared plus y squared just is equal to 25, and that allows me to simplify it down very nicely. I don't know why that did that, so let me try that again. Okay, now I've got my second derivative. I'll write it up here. Second derivative of y with respect to x simplified all the way down to negative 25 over y cubed. And now I can very easily evaluate that at 4/5. So let's go ahead and do that. Thus, the second derivative of y with respect to x at the point 4/3 is found by simply plugging 3 in for y, negative 25 over 3 cubed, or negative 25/27. All right, so that's a second derivative. So you take the derivative of the derivative, you then replace the derivative that shows up there from the chain rule with the derivative you found before. All right, so let's hit that last problem now. So here we've got the functions f and g. This is my f function and this is my g function. And there's some point P where the graph of f, on the graph of f at which the tangent line is perpendicular to g. So you're looking for something that's going to come in and kind of be perpendicular. Where would that happen? All right, well, we know that slopes come from derivatives. So let's take a look at the derivative of f, which is 1 over 2 radical x, and the derivative of g, which is negative 1. Now, if we want the tangents to be perpendicular, then we want opposite reciprocal slopes. So what I'm going to do is I'm going to take my f derivative, 1 over 2 radical x, and I'm going to set it equal to the opposite reciprocal of -1, which is just 1. So cross multiply, 2 radical x is equal to 1. Divide both sides by 2. Radical x is 1/2. Square both sides. X is 1/4. So on this graph here, 1/4 is about right there. So if we were to draw in a tangent about right there, that looks like a reasonable answer. It looks like it might hit that perpendicular. Now it does say find the coordinates of the point P. I have the x coordinate. I now need the y coordinate. This is a point on the graph of f. So I just find now f of 1/4, which is the square root of 1/4, which is 1/2. Thus, the coordinates of the point P I'm looking for are 1/4, 1/2. All right, so there you have it. Implicit differentiation with a little bit of review in there. Just remember, the important thing, when you're taking the derivative with respect to x of something that doesn't have x's, something that has maybe y's instead, you're going to take that derivative the way we always did. Derivative of sine is cosine. Inside stays inside. But now, because these don't match up due to the chain rule, you have to multiply by that extra dy dx. All right. Thank you for watching, and have a good one.